Hi. Okay, on my CPU build I've said I want to wire a controller into it at some point because I've got a goal to develop a couple of basic games for it. And I've always been thinking about the kind of classic 9-pin joysticks that I used to plug into my Spectrum and Ava home computers. But the 8-bit guy has been talking about his new kind of retro computer build, which is a 6502 derivative based system. And he's talking about using NES controllers. And a few comments from people said they were quite easy to interface to, and they do have the advantage over the old style joysticks that they support more than the 2 buttons that they all had. So I thought it would be worth taking a look and experimenting with one of these things. Now, the NES controller has a 7-pin connection, although some of the pinouts list 2 of the pins as unused, and some call those 2 pins D3 and D4, but I've not seen them used. I did look for a supplier for the connectors to plug these into, and they were all actually comparatively expensive. But I did find extension cables quite cheaply, and so I've broken out the wires onto a DuPont connector after chopping it in half. Well, that's interesting. These are the same make of breadboards as I've had before, but they've changed it. The red and blue lines are now unbroken, so I no longer need to bridge the gap between the 2 halves. I like it. Now, the way this controller gets 8 separate signals over less pins is it uses a shift register. So the power and ground are obvious, but then we've got a clock line, a latch line, and a data line. So these are basically wired directly into a parallel to serial shift register. So the idea is we raise the latch line, which will sample the 8 inputs, and then each time we cycle the clock line, it will output a different bit of that 8-bit value into the data line. So firstly, I'm going to need a clock. Now, this is the 555 timer. I'm not going to go into the detail of how the clock circuit works with this. The first video in my CPU build does a little bit more on that. I'm going to use a second breadboard here for temporary output. Slight mistake there, but I found it. Okay, I've used 330 ohm resistors and a 47 microfarad capacitor here, so I'm hoping that will give us a decent range on this little mini 5K pot. Yeah, it looks pretty good. Okay, now to make the shifting out work, we need to be able to generate that latch signal 1 in every 8 ticks of our clock. So I'm going to use an LS193 for doing that. Now, this isn't necessarily the best chip, but these are the up-down counters that I was using in my address registers, and I've got a whole bunch of these lying around doing nothing. Okay, so master reset needs to be low. Parallel load needs to be kept high because it's active low. We want to keep count down high. I'm not going to be using that at all. Count up needs to come from our clock. Let's take a look at this and see if it's working. So, bit 0, bit 1, and bit 2. Looks like binary counting to me. Now we need to generate a signal for every 8th clock. So we could do that by doing a logical AND on these 3 bits. So this is the LS08 AND chip. It's got 4 2-input AND gates. Now we kind of need a 3-input AND gate, but we can create one of those using 2 2-input AND gates. Let's check the output of that. So that should be flashing 1 in 4, which it looks like it's doing. So if we take the output from that AND gate and feed it as one of the inputs into the next, and then grab that 3rd bit. So yes, that's giving us our little pulse every 8 cycles. Right, so I'm going to feed that into the latch line on here, and we should have some kind of data coming out. Okay, this LED's come solidly on. And it went off briefly when I pushed that button. Okay, it's definitely going off at a later and later time as I progress along these buttons. It looks like we've got good data there. Okay, so now let's think about how we can decode it. Now, looking at serial to parallel shift registers, I came across the 74LS595. Now this isn't actually one of them. This is a 74HC595. It's the CMOS version, because these were a lot easier to get hold of. So I'm hoping that the kind of clock frequencies and stable voltage lines we're dealing with here, they're going to be pretty much the same in operation. Not 7 of the data lines happen along the bottom. And the 8th comes out over here. Okay, this is the first time I've used one of these, so I need to decode it a little bit. Pin 13 here seems to be output enable, so that's active low, so we'll pull that down. Now, SIR, I think, is serial data. It's come from over here. That wire's barely long enough. Now, SR clear, I believe, is clear, so that suddenly had an effect. So we have RCK and SRCK. SRCK, I believe, is the clock. Pick that up from where it goes into the counter. And this would make this. That looks promising. This will make this the latch, which needs to come in the output for our AND gate. Apologies for not having carefully cut wires for all of this, but these ones were obvious, but these I'm kind of making it up as I go along. Okay, so let's push a button down. Okay, 2 lights have gone off. That's not what I was expecting, but that's that was definitely in response to me pushing the button. Okay, and a different two lights, but with one overlapping, have come off when we've done that. Let's turn the clock up. Okay, that's weird. We get two lights for each button. That's not what we're supposed to get. Could probably still decode that in software, but it's not ideal. Okay, is this a problem with the outgoing signal or the processing of the incoming signal? This is the clock. And then this is our latch, 1 in every 8 clocks. Okay, that was definitely off for 2 clocks there. Okay, I think what's going on is kind of interesting. We take the clock into the counter and we use that same clock to output for controller and output into the latch chip, and we're counting away for a cycle of, well, 16, but we're only looking at the bottom 3 bits. We're looking at a cycle of 8, and we take the bottom 3 bits and we pass it into this AND gate, and then the result of that with the 3rd bit into this AND gate, and we get this same kind of digital square wave output here, but it's going to be slightly delayed from the clock. And I think what's happening is the square wave is overlapping 2 clock cycles just by a tiny amount. But if the latch chip in here is looking at the latch signal as a active high and rather than on the rising edge, then that's going to produce a bad result, because it's will be partway through, we have a shift overlapping with the latch signal. See if we can shorten it. What I'm going to do is put the result of that final AND, I'm going to AND it with the clock. Yeah, so it's just on for the first half now. That looks promising. Let's speed it up again. Yeah, that's all 8 buttons working. Okay, so these lights, well, the outputs are clearly active low. I'm going to switch this around because it will just make a little bit more sense to us. Okay, I think we're fully working now. Yes, that's all 8 possibilities here separately light up a different LED. We'd obviously interface this back to a bus with a line driver, and we can use an inverting one to give us the Nice positive going signals. I'd say we are currently updating this at, I don't know, what's that, about 4 Hertz? I really do need a scope at some point. But so that would be pretty horrible for controlling a game like that. You can see there's a visible delay between me pushing the buttons. So we should increase the clock rate a bit further. This is a 47 microfarad capacitor. Now, my understanding of the formula for the 555 timer is the frequency is roughly linear to the capacitance. So if I halve the capacitance, it should double the frequency. So I don't want to use the 100 nanofarad, I'll use the 150. I use those for lots of things. I should have a couple of these on this board. Yeah, so 150 nanofarad. So this is roughly 313 times lower capacitance. So it should increase the clock rate by a factor of 313. Which, if I was correct in my estimate of about 4 Hertz, that should be about 1.2 kilohertz. So yeah, essentially instantaneous. This is all irrelevant now because we're never going to see the lights flash. Easy LEDs are more suited to these 470 ohm still arrays. We've only got one now, spare. It's better. Okay, that circuit is working. It would only take me a line driver to interface this to my processor build. It's probably a little way off before that will be relevant, but nice to get ahead on some things. I'm really happy with this. That's pretty cool. I'm definitely going to use it. Alright, thanks for watching.